Assalamu alaikum dear students. I welcome you to the 16th lecture of probability and stochastic processes. We have gone through 15 lectures, which means 1/3 of the course is gone. And I hope by this time you have a good feeling of this course, the problems it addresses, the tools it uses to solve those problems. In recent lectures, we have been dealing with continuous random variables, and we have been trying to find probabilities of events defined for those continuous random variables. We dealt with uniformly distributed random variable, which is defined for a finite extent of real line, and the PDF or the likelihood as the x varies is a flat function with height 1 over the extent. It should be clear that uniformly distributed random variable can only be defined for a finite interval of real line. It cannot be defined for an infinite interval of real line. After uniformly distributed random variable, we dealt with exponentially distributed random variables. The exponential random variables are defined for an infinite interval of real line, particularly the positive values of real line. So, exponentially distributed random variable can take any value from 0 to positive infinity. And the PDF for exponentially distributed random variable is of the form, if x is random variable, then the form is lambda times e raised to power minus lambda x. After exponentially distributed random variable, we dealt with another similar random variable which had PDF of the format lambda square time x time e raised to power minus lambda x. I did not give it a name, but the fact is that this is a special case of Erlang type random variable, and this represents inter-arrival times of more than one independent arrival times. So we have dealt in detail with 3 types of continuous random variables: uniformly distributed, exponentially distributed, and Erlang type. Then we just touched the Gaussian random variable. One more thing about Erlang type random variable is that it is also defined for the positive real line, and the Gaussian random variable is defined over the entire real line. So the Gaussian type continuous random variable can assume any value, positive or negative, so it is defined for the whole real line, and the PDF for a general Gaussian random variable which belongs to a family of Gaussian random variables is k times e raised to power minus lambda x square, and x can take any value from minus infinity to positive infinity. One more thing about this Gaussian random variable is that it is symmetric. Because of the format of PDF, it is symmetric across y is equal to, across the y-axis, across x is equal to 0 line. So Gaussian random variable is defined over the whole real line, and it has PDF of the format k times e raised to power minus lambda x square, and it was shown to you that this k is equal to square root of lambda over pi. So if you use this as k, the total area under the Gaussian curve, which is square root of lambda over pi times e raised to power minus lambda x square, the total area under this curve comes out to be 1. By using different values of lambda, you can have different members of this family of Gaussian random variables. And in the slide that you will see, there are 3 such Gaussian random variables. The top portion of the slide shows the PDF of the 3 Gaussian random variables which were drawn for lambdas being 1, 2 and 4. The Gaussian random variable with lambda is equal to 1 is drawn in red. The Gaussian random variable with lambda is equal to 2 is drawn in green, and the Gaussian random variable with lambda is equal to 4 is drawn in blue. As you can see, as the lambda increases, the value of this PDF at x is equal to 0 in the center increases, because the value is square root of lambda over pi. For lambda is equal to 4, lambda over pi is larger than 1, its square root will also be larger than 1, and you see that the peak of blue PDF is higher than 1. But for the other two values of lambda, 1 and 2, lambda over pi is smaller than 1, its square root is also smaller than 1, and the peaks of these two PDFs is smaller than 1. So, higher the value of lambda for the case of Gaussian random variables, higher the peak at the center. But when the peak is higher, to keep the total area equal to 1, the PDF falls off quickly. For higher values of lambda, the PDF is a narrow, peaky kind of waveform. And for smaller values of lambda, the PDF is a narrower, broad type of waveform. The lower part of the slide shows the three CDFs for the three PDFs shown in the top portion of the graph. And you can see that for higher values of lambda, which gives a PDF which is a narrow and peaky kind of waveform, its parameterized integral, which is CDF, rises steeply and rises in the short duration, the duration which is the significant part of the narrow peaked region of the PDF. Similarly, for smaller values of lambda, the CDF rises slowly and rises over a broader region, and the broader region represents the broad region where the PDF is significant. Please note that to get CDF from PDF, we need integration, and for this Gaussian type of PDF, the integration, the parameterized integration, cannot be solved in a closed form. So we need to have numerical integration and other tools to get to CDF, or if you want to find probabilities defined for certain events on this Gaussian type random variable, you still need those numerical tools, because to get probability of an event from PDF, you need to integrate the PDF over the interval over which the random variable takes on values for that particular event. And as I said, the Gaussian PDF cannot be integrated in a closed form. You cannot have a closed expression in terms of x to get the PDF of different events or CDF from the PDF. Hence, you always rely on numerical techniques to find probabilities of events defined on Gaussian random variables. Let's look at an example which shows how a Gaussian modeling can be used to represent real life phenomena which is unpredictable, and how Gaussian distribution and the numerical techniques can be used to find probabilities of certain interesting events defined on such random phenomena. Suppose you are asked to hit a thin horizontal line drawn in front of you. So you are standing in a room or in front of a tall vertical wall, and on that wall there is a thin horizontal line in front of you, and you have a tennis ball and you are standing a certain distance away from that wall. You are not standing very close, say 20 feet, and at 20 feet you are supposed to hit that horizontal line. So you throw the ball on the line, but you are a human and you cannot accurately hit the ball all the time. But if you try hard enough, it is more likely that you will hit a point which is close to line either slightly above or slightly below compared to likelihood of you hitting the ball much higher point or much lower point. So the outcome is the vertical distance measured from that horizontal line, and we can have this vertical distance positive if you hit a point above the horizontal line, and we can have this vertical distance negative if you hit a point which is below the vertical line. We are not interested in the horizontal location of the point that you hit. We are only interested in the vertical displacement of the center of the point where you hit the ball measured from a thin horizontal line. So the range of this random observed phenomena is positive values and negative values for a certain range. You can have a large range considering those rare instances where you hit the ball, it slips out of your hand and it hits much below the horizontal line. So the total range of observed values include both positive and negative values, and it is more likely for you to hit a value which is close to zero in the center of the distribution. Hence, this real life unpredictable phenomena, which is the observation of vertical distance of the actual point that you hit when you are aiming on a horizontal line, can be modeled as Gaussian random variable. Let's draw this Gaussian PDF and try to find probabilities of a couple of interesting events for this random unpredictable phenomena. If you see on your screen, you will see a slide which shows the PDF has a peak at 0 and it tapers off as we go away from this 0 point, implying that it is more likely for you to hit the line than hitting a point which is much away, over or below the line. Let's find the probability of event that the point that you hit lies within plus minus 5 centimeter from the line. I have assumed for this Gaussian random variable to have a value of lambda equal to 0.01. With this value of lambda, I have drawn this PDF, and on this PDF I want to find probability of this random variable lying between -5 and +5. On the slide, this is represented as the red region on the PDF. So the area in this red region can be found using numerical techniques, and I have used those numerical techniques, and the area comes out to be 0.52. So there is a 52% chance that the point that you hit will lie between plus minus 5 centimeters from the horizontal line. Let's find probability of another event, that is that the point that you hit will be at least 15 centimeter away from the target. So you try to hit the horizontal line, and this event represents that the ball will hit a point which is 15 centimeter below the line or even further below, or 15 centimeter above the line or further higher up. This represents the tails, the two tails of this PDF. The first tail to the right is from 15 centimeters to all values which are larger than 15 centimeter. And the tail on the left side is representing the points which are at minus 15 centimeter or even more minus, which represents points below the line. So using numerical techniques again, the total area under these two tails comes out to be 0.034. So there is a 3.4% chance that the point that you are going to hit will be at least 15 centimeter below the target or at least 15 centimeter above the target. So you saw that PDFs and CDFs can be used to find probabilities of interesting events defined on different types of continuous random variables. You can do much more than just finding the probabilities of different events, and we are going to consider next what else you can do with PDFs and CDFs of continuous random variables. I hope you remember our discussion of expected value of a random variable when we were discussing the discrete random variables. In that discussion, we modeled the expected value of a random variable as a net torque on a thin rigid rod which is pivoted at 0 point, and then there are weights hanging on this rod, hanging with threads at points where the random variable assumes values, and the value of the weight is proportional to the probability of that random variable assuming that particular value where the weight is hanging. This analogy can be extended to continuous random variables as well. So, if you have a continuous random variable which is defined for a certain range of real numbers, then you build a thin dam or wall with height proportional to the PDF of the random variable. And then you let this thin constant width rod pivot at origin. So you pivot the rod at origin and build a thin dam on this rod where the height of dam at different locations represents the height of PDF function. Then the net torque on this rod is equal to the expected value of this continuous random variable. So if the rod is trying to tilt in a clockwise manner, you have positive expected value, and if the rod is trying to tilt in a counterclockwise direction, you have a negative expected value of this continuous random variable. The discussion about this rod getting nicely balanced if you pivot it at a point which is the expected value of the random variable also holds true for the case of continuous random variables. So you have a thin constant width rod, and on that rod you have a wall with heights representing the PDF, and if you pivot this rod at a point which is the expected value of this random variable, the rod with this continuously distributed weight should nicely balance itself. It should neither tilt in a clockwise manner nor in a counterclockwise manner. So how do you actually compute the expected value, which is also called mean of a random variable, if you have PDF? It turns out that it is just a simple extension of the summation notation we used for the case of discrete random variable, and the extension is to get the value through integration, because now the weights are not at isolated points, they are continuously distributed in the form of a wall. So to find expected value of a random variable, you integrate the parameter x with a weighting function, and weighting function is of course the PDF. So expected value of a random variable x is integration over the range where x is defined, integration of x times the PDF. So x fx dx, that is the expression you use to find the expected value of a continuously distributed random variable. Let's find out what will be the expected value of a uniformly distributed random variable which is defined from point A to point B. So this uniformly distributed random variable only takes on values between A and B, and the PDF is a constant height function with height equal to 1 over B minus A, assuming B is larger than A. It is simple integration, and you can find out that the expected value of a uniformly distributed random variable defined between A and B is equal to B plus A divided by 2, or the midpoint between A and B. So if A is 1 and B is 9, the midpoint is 5, 9 plus 1 divided by 2. So if your uniformly distributed random variable is defined from 1 to 9, you can pivot this at 5 and the rod will balance itself nicely, assuming that the rod itself has no weight. It's the weight of this PDF that causes the tilt. This is not unexpected, because when you pivot a uniformly distributed random variable represented by a wall, at the center point half of the weight is on this side, half of the weight is on this side, and all these distributed weights cancel each other out and the rod gets balanced nicely. Let's look at the expected value or mean of other continuously distributed random variables. Let's start with exponentially distributed random variable. The exponentially distributed random variable, whose PDF is given in the form of lambda e raised to power minus lambda x, has a mean value which is given by 1 over lambda. So if you choose different values of lambda, the shape of the PDF changes, so does the location of the mean value or the expected value. This is shown in the slide that you can see, where 3 exponentially distributed random variables are shown on the top portion of the slide. These random variables are shown in red, green and blue, and they used lambda values of 0.5, 1 and 2. The exponentially distributed random variable with lambda is equal to 0.5 is shown in red, and it has the expected value of 1 over 0.5 or 2. So this is represented with a thick vertical line at 2, shown also in red color. The second member of the exponentially distributed random variables was drawn with a lambda of 1. This is shown in green, and the location of its mean value is also shown with a thick green vertical line at 1. And the last member of the exponentially distributed random family, shown in blue, had a lambda value of 2, and the location of its mean is at 1 over 2, which is 0.5. If you look closely on this slide, you will see that this is exactly as expected. For the blue distribution with lambda is equal to 2, a lot of weight or sand is close to the origin, and the pivoting point has to be close to this origin so that this accumulated sand close to the origin balances out the tail of blue region, which falls off quickly and has very less weight on the right side compared to other two distributions. Similarly, if you compare this blue distribution with red distribution, which has a lambda of 0.5, you will see that the red distribution does not have a lot of concentrated weight towards origin. So it has less weight on the origin, and it has to have its balancing pivot point at 2, so that some mass gets on the left of the pivoting point and the remaining tail, which decays slowly, gets on the right of the pivoting point. So this set of 3 graphs is intuitively very clear, and it shows as the shape of the distribution changes, so does the location of its mean or expected value. The lower part of the slide also shows 3 PDF functions. These PDF functions are from the Erlang type random variables, and they are also using the same 3 values of lambda, 0.5, 1 and 2. It is very simple mathematical calculation to find the mean value of Erlang type random variable, and for an Erlang variable with parameter lambda, the mean value is 2 over lambda. So for these 3 random variables with lambda is equal to 0.5, 1 and 2, the mean values are located at 2 over 0.5, which is 4, 2 over 1, which is 2, and 2 over 2, which is 1. So the location of these expected values are different compared to the location of expected values of exponentially distributed random variable. That's why they are drawn on the same slide, one over the other, so that you can compare the shapes of the distributions and have a clear idea how the shape of the distribution affects the location of the balancing pivot point or the expected value. If you look at the three graphs on the lower part of the screen, you will see that the red distribution has much less sand towards the origin, hence its balancing pivot point has to be at 4, much away on the right side, and the blue distribution with lambda of 2 has some sand closer to the origin, hence its balancing pivot point comes closer to origin at value of 1. So we have used PDFs and CDFs of continuous random variables, and we have used them to find the probabilities of interesting events as well as the expected values of the random variables whose PDFs are given. Now I'm going to recall the discussion that we did on the discrete random variables, and in that discussion I said that if you want to find the expected value of a transformed random variable, you don't need to have the PDF of the transformed random variable. For calculation of expected value of a transformed random variable, say y, which is obtained from a random variable x through a meaningful transformation, all you need is the information about this transformation and the PDF of the original random variable x. So you don't have to find the PDF of the transformed random variable. All you need is PDF of the original random variable and this function which transforms random variable x to random variable y. And for this case, the expected value of y is equal to integration over the desired range of the transformation and the original PDF. So if y is obtained from x through transformation which is called g of x, so g is the transformation, then the expected value of y can be obtained by integration of y times PDF of y, or y fy integrated over the range. Or you can have the same answer by integrating over the range of x and integrating not x fx but g of x times fx. So if you integrate g of x times fx over all the values of x where the x takes on its value, you get expected value of y. This is simple, and you can use this to find the expected value of transformed random variables. Suppose the transformation is very simple, something like y is equal to x plus c, where c is a constant. So what are you doing? You are taking the observation of x, and instead of using that observation, you are adding a constant value to that observation and using that transformed value. So if you add a constant value to every observed value, you are changing the expected value of the random variable by the same value c. And it's easy to see because this addition of c is a linear function, and this addition simply translates to the expected value of y being equal to expected value of x plus c. We can use this information to have Gaussian random variables which are not symmetric around origin. They are not symmetric around x is equal to 0 line or y axis. They are symmetric around some other point. For example, you can have a large population of, say, boys, and you pick a boy randomly and observe its height. This height will not be a negative number. It cannot be. Height is always positive. But this height will be close to what you expect the height to be. What is the average height of a population of boys? Suppose that the population has a mean value of 175 centimeters. So it's more likely for the picked boy to be 175 centimeter tall. It can be 180 centimeter, it can be 169 centimeter, but it is more likely for the randomly picked boy to have a height of 175 centimeter, and it is less likely for this boy to have heights which are much higher than this mean value or much lower than this mean value. So how do you get PDF of such a random variable which is not symmetric around the y-axis? You simply get this distribution by adding a constant value to a distribution which is symmetric around y-axis. So I have used this type of shifting of a Gaussian, and this shifted Gaussian is also a Gaussian. The only difference is that its mean is not 0, its distribution has been shifted. Instead of writing the expression of this PDF as k times e raised to power minus lambda x square, I should write it as k times e raised to power minus lambda, and then in the bracket x minus c whole square. This x minus c shifts the mean to right. So this shifted distribution can be used to solve problems of real life. Let's revisit that problem of randomly picked boy and its height varying around the mean. I have drawn the PDF representing the height distribution of boys on the slide, and to make the problem more interesting, I have also included another PDF which is also a shifted Gaussian, but this represents the height distribution of girls. So if you have a large population of boys and girls and their height distribution is represented by two Gaussian distributions, where these two Gaussian distributions are not centered around y is equal to 0 but centered around the population mean, the average height of boy in the case of the distribution of boys and average height of girls in the case of distribution of heights of girls. These two PDFs has been sketched on the slide that you can see, and on this slide the distribution of height of boys is shown in red, and you can see it has a peak at 175, which is the mean height of boys, and this PDF has been drawn with a lambda of 0.005. Next to it there is a blue Gaussian curve with mean at 165, and this represents the height distribution of girls with a mean value of 165. This mean value of 165 was chosen to follow the common perception or the fact that usually the mean value of girls is less than the mean value of boys' heights. So I have assumed the mean height of girl population to be 165 centimeters and mean value of boys' height to be 175 centimeters. I have also used different lambdas for the two distributions. For the distribution of boys, I have used a lambda of 0.005, and for girls I have used 0.008. Because of this higher value of lambda, the distribution representing the girl's height has a higher peak and it is narrow in shape, whereas the distribution representing boys has a lower peak and it is slightly broader. If you want to find probabilities of different interesting events on this type of real life distributions, then you have to be careful. We have shifted the distribution to the right to represent the mean value of the average height that we observe among the population. But this PDF, which is shifted Gaussian, is still defined for the whole real line. Even though we know that it is impossible for a boy to have a height of 12 meters or a height of -3 meters, but this shifted PDF is still defined and has non-zero, although very small values of probability for this random variable to be 12 meters or minus 3 meters. So you should know that even though these values are out of question, we are using the shifted Gaussian distribution to approximately represent the distribution of heights of boys and girls. If you use your lambda carefully, then these distribution will fall off quickly and they will very close to zero line in the useful range. So if you think that it is impossible for a boy to have a height less than say 90 centimeter or more than 2.5 meters, then you should choose a lambda where the Gaussian distribution has a peak at 175 and it falls off to sufficiently low values by the time it reaches 2.5 meters on the right or 90 centimeters to the left. With this clarification, let's move on and find probabilities of some interesting events for this pair of distributions. If you look at the slide, you will see that the first event that I am interested in is that what is the probability that the randomly picked girl will be of height between 165 and 175 centimeters. These two numbers are mean heights of girls and boys. So what's the probability that you pick a girl randomly and her height starts from 165 and ends at 175, or her height is between 165 centimeter and 175 centimeter, or the girl is taller than an average girl but shorter than an average boy. You can once again use numerical techniques and you can find this probability to be 0.397. You can ask the same question about boys, that what is the probability that a randomly picked boy has a height which lies between 165 and 175 centimeters. Or in other words, you want to find the probability of the event that a randomly picked boy is shorter than an average boy but taller than an average girl. You can once again use the numerical techniques and you can find this probability to be 0.341. By the way, these two events are shown on the slide as blue hatched area using vertical lines, which is the event representing the girl being between 165 and 175 centimeters, and the other event is represented by the red hashed area with horizontal lines, which represents the boy being of height between 165 and 175 centimeters. Let's look at the slide to find probabilities of two other interesting events. What is the probability that a randomly selected girl is taller than 185 centimeters? I have picked this 185 arbitrarily. You can use any other value to find such probabilities. Anyway, the probability of this event is shown as the solid blue tail of the blue distribution to the right. And this area, the solid blue area, represents the probability of a randomly selected girl being taller than 185 centimeters. And this area is very small and this probability comes out to be 0.006. So there is less than 1% chance that if you have such a population and you pick a girl randomly and she comes out to be taller than 185 centimeters. Let's ask the same question about boys. What is the probability that a randomly selected boy is taller than 185 centimeters? You know that this probability should be larger than 0.006 because in general boys are taller than girls. But answering this question in a mathematically precise manner requires the use of probability theory, the modeling of unpredictable phenomena using PDFs, and then finding the probability of such event using the required tools, which in this case is numerical integration. This event of a boy being taller than 185 centimeters is shown with solid red area, but it also includes the solid blue area. So the total of solid red and solid blue area represents the total area under the red distribution from 185 centimeter to all the positive values. And this probability comes out to be 0.16. So there is a 16% chance that a randomly picked boy will be taller than 185 centimeters, and there is only 0.006 probability or 0.6% chance that a randomly picked girl will be taller than 185 centimeters. What else can you do with distribution functions of continuous random variables in addition to finding probabilities and expected values? We are going to repeat the discussion that we did for discrete random variables, and the next thing we are going to consider is higher moments. Higher moments are the weighted integrals of higher powers of the parameter representing the values attained by random variable. So if random variable is x and the values it attains are represented by small x, then the second moment, the simple one, is integration of x square over the range where the x attains its values, but this integration of x square is weighted by the PDF. So integration of x square fx is simply second moment. It's called simple second moment because it takes the PDF and takes the values and just squares the values of the random variable, multiplies it with the PDF at that point and use that expression in the integration. So you can have second, third, fourth moments and even higher moments, and you can have other type of moments which are called centralized moments. If the random variable is zero mean, then the simple moment and centralized moment are same, because centralized moments are defined for a transformed random variable which has zero mean, and this transformation, as you can guess, is nothing but subtraction of mean from the observed value. So if you have a random variable x which has a mean value mu x, you use a random variable y which is x minus mu x, and this random variable y is zero mean, and you take second, third, fourth moments of this random variable y, and they represent central moments of random variable x. Let's try to find some higher moments, and one of the higher moments is very important. It is called variance, and this variance is centralized second moment. So let's look at the variance of a few continuous random variables that we have been dealing with. Suppose we have a uniformly distributed random variable, and to make life simple, we'll assume that it is zero mean. So this uniformly distributed random variable takes on values from minus a to plus a. So it's uniform with height of 1 over 2a, and the extent is from minus a to a. Since this is zero mean, all you need to do is find the second moment, and it will be variance. If you do elementary integration that is needed for this case, you will find that the variance of a uniformly distributed random variable which takes on values from minus a to plus a comes out to be a square over 3. So if a is large, the variance is large. If the random variable is uniform but thin, defined over a large range, if a is say 100, so it is defined from minus 100 to 100, then its variance is large compared to another uniformly distributed random variable which is defined from minus 5 to 5. So for uniformly distributed random variable which is from minus a to a, the variance is a square over 3. Let's move on to the next continuous random variable, that is the exponential random variable. This exponential random variable is defined for all positive values of x, and its PDF is lambda e raised to power minus lambda x, and it has its mean value which is not 0. So you have to subtract the mean value while you are trying to find the variance of exponentially distributed random variable. If you do what is required, and at the end of integration you will get that the variance of exponentially distributed random variable is 1 over lambda square. So if the starting PDF is lambda e raised to power minus lambda x, then the variance of this random variable is 1 over lambda square. Similarly, for Erlang type random variable which has a PDF of lambda square x e raised to power minus lambda x, the variance comes out to be 2 over lambda square. And lastly, if you take a Gaussian random variable which is defined in terms of lambda again, and if it has a PDF of square root of lambda over pi e raised to power minus lambda x square, then the variance of such Gaussian random variable which is zero mean comes out to be 1 over 2 lambda. So all you need to do is do elementary integrations, and you can find higher moments, expected values, and other interesting parameters of the random variables. Let's continue with our discussion of higher moments, and we are interested in this question that suppose you have a random variable x and you know its PDF, so you can find its mean, its higher moments, particularly variance, and if you get a new random variable y from this random variable x through a transformation, and you want to find the variance of this transformed random variable. The question is, do you need explicit information about the PDF of y? If you had that information, then you can certainly use that PDF to find whatever you want to find, mean or other moments. But is it possible that you don't have to find the PDF of transformed variable and you can use the PDF of the original random variable to find the variance and other things? The answer is yes, and in a certain case where the transformation is linear, the answer is readily available and you don't have to even do any calculation to find the variance of the transformed random variable. Suppose the transformation is of the kind which is translation, that y is equal to x plus c. So if this is the kind of transformation, then the mean of the transformed random variable is the mean of the original random variable plus c. But variance does not change. Why? Because if you have transformed this random variable in this way, then the mean has shifted, but before you want to find the variance, you have to subtract this new mean from the observed values, and the variance is always calculated on zero mean random variable. So if you transform a random variable with constant addition, the variance does not change. What if the transformation is of this kind? Y is equal to m times x. If you remember our discussion of discrete random variables, then this type of simple linear transformation either expands the distribution or contracts the distribution. And in case of discrete random variable, just the locations of the random variable move, the heights do not move. But in the case of continuous random variables, if the distribution gets expanded or contracted, then the height should also change so that the total area remains 1. In any case, if you do the required elementary integration, then you will see that the variance of the transformed random variable is very easy to find. If y is equal to m times x, then variance of y is equal to m square times the variance of x. All you need to do is sit, take pencil and paper and integrate the variance of y, where y is m times x, and it is a simple process to come up with this conclusion that for the case of this type of linear transformation, y is equal to mx, the variance of y is equal to variance of x times m square. What about a completely linear transformation like y is equal to mx plus c? The mean gets shifted, but the variance is only controlled by m. Even in this case, the variance of y is equal to m square times the variance of x. So, if you have such a simple linear transformation, it's easy to find the variance of transformed variable. All you need to do is multiply it with m square, where m is the constant multiplier which is used to get y from x. This information is used to represent the Gaussian random variables in a standardized format. You see, I told you that to get to probabilities of different events on Gaussian distribution, you have to do numerical techniques. You have to use numerical integration. And it will be tedious to use numerical integration for all possible values of lambda and all possible values of mean. So if you are given a random variable which is Gaussian, which has a non-zero mean, which has a certain variance, which is lambda, which is not lambda, it is a function of lambda. So if you have a Gaussian random variable with non-zero mean and a certain variance, all you should do is transform this random variable to a zero mean unit variance Gaussian random variable. And your event defined on the original Gaussian random variable also gets shifted, its location, its extents get changed, and the probability of original event can be found from the PDF of this zero mean unit variance Gaussian distribution by using appropriately shifted limits. And books represent this type of unit variance zero mean Gaussian random variable very thoroughly, and they gave the numerical values of different events, and this is usually given as error function, where error function is defined as integration of unit variance zero mean Gaussian curve from 0 to a certain value of parameter, and for different values of these parameters the results of this numerical integration has been tabulated. So if you look your textbook or any other reference, you will find that the Gaussian probability distribution has been integrated numerically using this error function type of functions, and you can use these tabulated values to find probabilities of different events. Today we extended our discussion of continuous random variables and found the expected values and higher moments of uniform, exponential, Erlang and Gaussian random variables. In coming lectures, we are going to move beyond a single continuous random variable and will deal with two or more continuous random variables. Till then, I wish you the best. Khuda Hafiz. Assalamu alaikum.